X equals A dot B represents this mathematically. To test this, we use a 7408 chip on our virtual circuit board. Injecting 5 volts into switch A while leaving B at 0 keeps the circuit broken. Closing both switches concurrently opens the gate, passing 5 volts to the LED. The AND gate establishes strict conditionality. The system only takes action when all physical prerequisites are met. By combining these simple operations, we get universal gates, NAND and NOR. A NAND gate is simply an AND gate with a NOT inverter permanently attached to its output. They are called universal because with enough NAND or NOR gates wired together, you can replicate every single basic logic function and Boolean expression possible. This creates a massive engineering advantage. Standardizing hardware to universal gates drastically reduces circuit complexity and lowers manufacturing costs. Rather than designing bespoke chips for every distinct mathematical operation, a fabrication plant can just stamp out millions of identical NAND gates. We see this extensively in practice. The address bus decoding in an 8085 microprocessor relies specifically on an 8-input NAND gate to generate enable signals. In that system, the NAND gate acts as a trap. It outputs a low signal to trigger the latch, only when a very specific targeted sequence of addresses are all universally reading high. Universal gates bridge the gap between mathematical ideals and industrial reality, making affordable, mass-produced computers physically possible. To perform complex arithmetic, we need exclusive gates. The most crucial of these is the EX-OR gate, often referred to as the inequality detector. Reviewing the student procedure for the 7486 EX-OR chip, the parameters dictate applying 0 and 5 volts specifically to test for inequality. The Boolean expression for an EX-OR gate requires the inputs to be strictly at different voltage levels to output a true signal. Returning to the virtual breadboard, we test this constraint. Applying the same voltage to both inputs yields a dead output, but applying mixed voltages, sending 5 volts to A and 0 to B, satisfies the condition. The LED illuminates. Because they isolate differences, EX-OR gates form the fundamental building blocks of arithmetic logic units, providing the actual mechanism computers use to perform binary addition. Its inverse counterpart is the EX-NOR gate, or the equality detector, which only outputs a high signal when both inputs match perfectly. When you scale this EX-NOR logic up, it allows systems to compare complex multi-bit numbers. This truth table for a 7485 chip shows a 4-bit comparator executing that exact equality check. Exclusive gates elevate simple physical switches into engines capable of executing real computational arithmetic and precise error detection.
Thank you for viewing so far. If it gives you some information, hit the like button and subscribe for more such technical learning.